Welcome back to part 2 of sections 16.5 and 16.6. I should say sections, I guess. You probably noticed that I'm wearing the same outfit as I was wearing in the first part of the video. And it's because my daughter and I are up in Beach 207 on a Saturday night at about 10 o'clock filming these videos. She's a real trooper. Thank you for helping me, Dee Dee.
You're welcome.
And so let's start with a very quick review problem. I just want to pick one of these compounds. Just write the balanced equation and the expression for the KSP, for the dissociation of these ionic compounds. Let's just do the PbCl2 in the middle. And so I'll do this one for us. Just to remind ourselves, we're dealing with the solubility of compounds in water. These are poorly soluble compounds. And so that's the balanced equation for this. And typically when we do our ice chart problems, that's what we're going to start with. And then we want to write the K expression for this. So we'll say KSP is the concentration of the lead 2 plus times the chloride squared because of the 2 in the balanced equation. And recall from earlier, SB stands for solubility product. So in this second portion of the chapter, we'll relate some of this to Le Chatelier's principle, which you recall from earlier in the course. Le Chatelier's principle states that if you take a system that's at equilibrium and you make some change to that system, the system will adjust and return to equilibrium. So it's things like removing products will give you more products, for example. And we'll look at 2 of these 3 applications. We're actually going to skip one of them. So application number 1 will be something called common ions. The second one on pH and solubility, we actually will not be covering. I'll tell you what slides to skip. And then the third one will be precipitation. We'll do a demonstration on that in a little bit, and they'll be asking the question whether or not something dissolves in water makes a solid when you mix 2 items together. And so like I said, we'll be skipping that middle one. I'll notify you what parts of your booklet to cross out. And so the first one is on common ions. I'm going to ask you this in a conceptual manner, and then we'll do some math on it. And so here's a reaction where calcium fluoride produces ions, calcium 2 plus, and a couple of F minuses. And so think about this for a moment. What are 2 ways that you can make this reaction go to the left? And so I'll let you mull it over. Good chance for you to pause the video. We'll come back with the answer. I want to make this go backwards. And keep in mind when you think about this, this material is a solid. And so if you want to make this go left, actually removing this would not help because it's a solid. The only 2 ways to actually make this go left would be to add some calcium ion via another water-soluble compound and add some F minus. And so the 2 ways would be add that calcium 2 plus or F minus. When we do the math in a moment, we're going to see the F minus will be put in. And so that's where the name common ion comes from. what we're doing is we're taking one of the ions already present, and we're adding more of one of them. You could use, let's say, a water-soluble compound, NaF, totally water-soluble. That would be a way to get some extra F- ions in there. Remember, the KSP is a constant. So when we do the math, if we increase the F, the calcium has to go down. It's the only way you can make a constant. So the equilibrium here will shift to the left by adding one of those two ions. So now let's do the math. So the solubility in pure water for calcium fluoride is 3.3 times 10 to the minus 4. Well, the solubility increase, decrease, or stay the same if we add some NaF. This is kind of combination of conceptual and mathematical. And so, in this case, since we're adding a common ion, you can pause the video now and think about it yourself. I'll reveal the answer. The solubility of the compound will decrease because the reaction goes to the left, some solid will fall out of the water. So solubility will decrease. And so you're adding F minus, the reaction will go backwards. What will happen to the KSP if we add some NaF, which produces F minus ions? Will the KSP increase, decrease, or stay the same? You can pause the video, think about it for a moment, maybe even say to yourself what the words that go with KSP are. That might give you a clue. So math-wise, set up here the KSP, or actually we don't have the KSP yet, we'll get it. The KSP will stay the same unless you change the temperature. KSP is a constant, solubility product constant, and so that will stay the same when we do an ice chart. The only thing we're going to change is the F's going to go up, so like I said, the CA will go down. And so here is some of the math involved, and you'll be given the KSP for a problem like this. This is the same problem in your book that's on 678. And so there is our balanced equation. The KSP is going to be given in this kind of problem. It's 1.44 times 10 to the negative 10. That is from the table on 675. It's going to be an ice chart problem. But when you do the first row, the initial line, the calcium will be 0. How about the spot where there's an F there? This time it's not 0, it's 0.1. And so that would drastically change our math. Change, we do the usual we're doing. This is plus X. The only way this reaction can go is to the right because there's a 0 on that side. Fluoride plus 2x. We add down the columns again, right? This is going to be x. This is 0.1 plus 2x. We're going to make a simplification in a moment because otherwise this one will get very sticky. And so KSP is given as 1.44 times 10 to the negative 10th. plus 2x squared. If we do a FOIL on that from algebra, we would end up with a cubic term, and it'd be very hard to solve. Just like we did when we did weak acids back in our previous material, we will be able to make the simplification in this problem where this value is going to be so small we can disregard it. Just like we did earlier, if you could state that the concentration of the common ion is greater than 100 times the K value. So if that's a true statement that if 0.1 is more than 100 times the KSP, then you can drop the 2x. And algebraically in our problems in this class, we really have to make it set up that way. And so the plus 2x disappears. This turns into 1.44 times 10 to the negative 10th equals x times 0.1 squared. And so now the new value of x, or in this case the x we get, is just the k divided by 0.1 squared. This is good practice for exams like the MCAT where you have to do some mental math. If you divide by 0.1 twice, you'll end up raising that exponent by 2 slots. And so the answer to this is 1.44 times 10 to the negative 8th. That's the solubility of the calcium fluoride under these conditions. It'll come out as moles per liter by default because we're working with a K value. And so that's the solubility under these conditions. We didn't do the other problem here, but if you did this in pure water, that's given in that previous slide. The solubility of that compound in pure water is 3.3 times 10 to the minus 4th. Under these conditions, it's 1.44 times 10 to the negative 8th. And so the solubility goes down by many thousands of times. If you were to divide these on your calculator, you'd get an answer that was about, looks like 20,000, I think. And so, or 200,000, maybe. Some 20,000. And so that's the amount the solubility decreases by adding a common ion. You can, if you increase this one will go down. That's the way constants work. And so the pH and solubility material will be skipped. To save time, we lost a week after spring break, and so I'm yanking out some bits of material along the way. So we're going to skip number 2 on this, and so then you would jump up to the middle of page 5 in the notes, and then we'll go to KSP application number 3 on the Chalier. And so you should be on the middle of page 5 on precipitation. And so this is very similar actually to precipitation when you think about rain. It rains when there's too much moisture in the air. In this case, a solid will form when you have too many ions in the solution. And then it'll come down as a solid instead of liquid rain. And so we're bringing back this concept of the reaction quotient. This goes back probably to chapter 14. So if we look at a reaction like this, the calcium fluoride reaction we've been seeing, where it makes the calcium ion and a couple of fluoride ions. The Q is calculated just like K, except that the concentrations may not be in equilibrium. And so the Q on this is going to be the calcium times the fluoride ion squared. And then we'll do our calculations based on values, and we'll review this in a moment, just predicting whether the reaction goes to the left or the right, or it's at equilibrium. And so keep in mind, concentrations may or may not be in equilibrium. When they are the same, then you have a perfectly saturated solution. And so this we covered back in chapter 14 when we talked about Q. If you go back in your notebook, page 8 of chapter 14, if you have the materials with you, or if you have a textbook, or you can just think about it as a review. When we look back, I'll do the bottom one. When Q equals K, you are at equilibrium. The reaction will have no preference to go left or right. It'll just be in that constant motion where it's at equilibrium. If Q is less than K or greater than K, think about filling those in. This is a good chance for you to pause the video, and then when you come back, I will reveal the answers that you hopefully have correct. Like I said, if you have your book with you, you go to 577. In your notes book, it's back in chapter 14. So when the Q is less than the K, that means there are not enough products. And so the reaction will go to the right. When you're dealing with solids, you would say that that solution is unsaturated because more could dissolve. Running out of choices for this one, when the Q is greater than the K, you have too many products, the reaction has to go to the left and solid will form. That's the question we'll ask in the next math problem. When this is great, if this is greater than the K, then the reaction has too many ions hanging around the solution, they grab each other, fall to the bottom. Dean wanted me to add a joke to this section. Here's a chance. There's an old saying, if you're not part of the solution, you're part of the precipitate. And so this is where a precipitate forms. She's laughing very loudly. And so we'll do a sample problem here, and it'll be involving calcium fluoride. Here's the KSP, 1.5 times 10 to the minus 10. And so then, in the problem here, you're given a couple solutions. The calcium is 0.04 molar in parts A and B. Let me even add that. And you'll be doing a Q versus K comparison. In part B also, we're going to have a different amount of fluoride ion, but once again, the calcium is 0.04 moles per liter. And then once we do the math on these, we will check it on a demonstration. This is one you would have been working in small groups, checking your predictions on this, but unfortunately, we cannot do that under these times. And so, pause your video on YouTube and try these problems where you're calculating the Q just like you calculated K, and then these are ultimately going to be yes or no questions. does it make a precipitate? Here's the first one. The Q on this, you can write the SP on the bottom if you want, doesn't matter. We're taking the amount of calcium, 0.04, times the amount of F minus, and then you have to square it. Because the expression is just like the K. You gotta square that. So this ends up going to the -12th. You times that by, multiply that by 0.04. And so you get a value of 4 to the -14th. That's the Q. You ask yourself, is that bigger than the K value? And the answer for this one, it is not bigger than the K value. This is an unsaturated solution. The solution can handle more ions. And so part A, the answer is no. I'll check it on a demonstration here. Nadine, can you look through the camera and see if you can see this?
I'll zoom out.
I can go over here. Okay, so this is a solution that contains some calcium ion in there. I can pick it up. And so this one we predicted actually it was a no. And so this one should not make a precipitate. And so that matches the prediction. We mixed these two solutions and the combination of them did not produce a Q greater than K, so then that one did not make a precipitate. Let's do the math on part B, and then we'll do the demonstration for part B. This time the Q equals 0.04 times F minus squared. But that gives you 1 to the -6. We multiply that out, and you get a value of 4 times 10 to the -8. That's Q. We compare that to K. If we mix these two solutions, there are too many ions in the two. When they mix, some of them will latch onto each other and fall to the bottom. And so this would be a yes. Let's check that prediction. Let's see here. Here's some calcium. It's better work, otherwise you should reshoot the video, Dee. And so then I add, in this one, I add the B. And so the solutions that I added were too concentrated. And so then the Q is greater than the K, and then I make this chalky precipitate. This is the calcium fluoride. It's kind of in a colloid right now, but eventually that'll settle to the bottom. But there are too many ions in that solution. So like I said, they grab each other, enough falls out until we get back to the value of the K. And so the way we'll cover this in this material, precipitation problems like this are really going to be yes or no questions. Q versus K. If the Q is smaller, you don't make a precipitate. If the Q is bigger than the K, make a precipitate. And we're actually going to skip the material on selective or fractional precipitation. That's the next two boxes. And so that's it for the material in this portion on sections 16.5, 16.6. We're just doing part of 16 here. So we skip that, skip the next slide that says sample problem. And so here's a quick summary of the chapter. KSP shows how much solid dissolves in water. And we're dealing with solids that just dissolve a little bit. This is a common ion effect. Adding an ion that is a product makes your reaction go in reverse. Ultimately, you're making the Q bigger than the K temporarily, and then it will make a solid. We skipped this material on the salts and weak acids. That was that second application, so don't worry about that. And then we're not really messing around with selective precipitation. We just really ask ourselves whether or not something comes out of a solution. So if you add a bunch of one ion, you can drop out the other one. And so that's just that third application. Pretty straightforward precipitation questions. So if you think way back to precipitation reactions, we made solids like that. In reality, a little bit of that solid dissolves, and that's based on the KSP value. And so I added 4 more book problems to the list I gave you in part 1. And so at the end of this chapter, you'll see some of these we've already considered. And so if we do a quick count on that, it should come up to 10 for this chapter. And so we've got 4, 6, we have 10. In my view, if you understand how to do these 10 problems for sections 16.5 and 16.6, you have this material covered and you should be fine. My goal for this would be by the end of this week coming up, March 23rd is Monday when all the classes go live. And so what I want people to do is watch the 2 videos, parts 1 and 2 of this material, try these 10 problems, contact me via email or text or Zoom or whatever, we can work through some problems. And then probably next weekend, I'll see where people are at, I'll talk to some people, and then I think we'll try maybe a homework assignment and a Blackboard quiz on this material. But honestly, if you understand these 10 problems, you should be fine. Director?
Cut.
We'll see you again.